Okay, think about this for a second. How can the exact same app run on your iPhone, your Windows laptop, and on some random server tucked away in a data center? It seems like it should be impossible, right? But the answer, well, it's one of the most elegant and powerful ideas in all of computer science. It's the unsung hero that makes our entire digital world work. So let's pull back the curtain and see how it's done. So, here's the fundamental problem we're up against. You've got dozens of popular programming languages. Python, Java, C++, JavaScript, the list goes on and on. And on the other side, you have an almost endless variety of computer hardware, and each one speaks its own unique machine language. The big question is, how on earth do you get all of these things to talk to each other without just complete chaos? I mean, if you tried to solve this the hard way, it would be a total nightmare. You literally need a unique translator, what we call a compiler, for every single combination. A compiler for C++ to an iPhone, another for C++ to an Android phone, one for Python to an iPhone. You see where this is going. The numbers get insane fast. It's called the M times N problem, and it is basically unmanageable. This is where our master translator, the compiler, comes in with a brilliant strategy. It's a way to break this impossible problem down into much smaller, manageable pieces. See, instead of trying to go directly from a programming language all the way to a specific machine, it introduces a really clever middle step. Think of the compiler's job as being split right in two. You have the front end, which is totally machine independent. Its only job is to understand the programming language, like Python. Then you have the back end, which is language independent. Its job is to write code for a specific type of machine. And the bridge that connects these two halves, that's our crucial middle step, intermediate code generation. So that crucial middle step creates something called an intermediate representation, or just IR for short. You might also hear it called intermediate code or intermediate language. Don't worry, they all mean the same thing. Just think of it as a kind of universal generic language that sits right in the middle between the human-friendly code and the machine-specific code. And I absolutely love this analogy because it just makes the whole concept click. The IR is basically a blueprint of your program. It's not written for a human tree, and it's not written for one specific computer chip. Nope, it's a perfectly detailed universal blueprint that captures the absolute essence of what the program needs to do. Okay, so you might be thinking, why go to all this trouble? Why create this extra blueprint? Well, it's because this approach gives us two massive advantages. Seriously, these two wins are what make all of modern software possible. First big win, portability. Remember that impossible M times N problem we talked about? Well, the IR blueprint just completely solves it. Now, instead of building a unique compiler for every single pair, you just need to build M front ends, one for each language, and N back ends, one for each machine. Then you can mix and match. Got a new language you want to run everywhere? Just build one new front end. It's so much less work, it's not even funny. And the second big win is optimization. This is so cool because the IR is this universal blueprint. It's the perfect place for the compiler to go in and make improvements. It can analyze the blueprint to get rid of redundant steps, rearrange things to be faster, and just generally make everything more efficient. And the best part? These improvements are machine independent, so that faster, cleaner code gets generated for every single target machine, automatically. Now, if you think that's clever, it actually gets even more interesting. It turns out this blueprint isn't just one single thing. Most sophisticated compilers today actually use multiple levels of blueprints, kind of like moving from a high-level sketch down to a really detailed plan. So you'll have a high-level IR, which looks a lot like the original programming language. This is great for understanding the overall structure. Then the compiler translates that into a low-level IR, which is much, much closer to what a computer processor actually understands. This is perfect for machine-specific jobs, like figuring out the best way to use the processor's memory. It's just like an architect's first concept sketch versus the final detailed construction plans. So when you put all of this together, you really start to see just how critical this idea is. It's not just some technical detail in a complex process. No, it is the key that unlocks the entire modern software world we live in. And that really is the big takeaway here. Intermediate representation is this brilliant abstraction that lets language designers focus on designing great languages and lets hardware designers focus on building amazing hardware. It's the universal translator, the master blueprint. It's the silent, unsung hero that allows our digital world to actually work, connecting all those languages to all those machines seamlessly.
And that leaves us with one last thing to think about. This whole incredible system works because we found the perfect middle ground, the right intermediate level of abstraction to solve what seemed like an impossible problem. It really makes you wonder, doesn't it? What other huge challenges in technology, or maybe even somewhere else, are just waiting for us to find their perfect blueprint?